So good morning, guys. Today we're going to start jumping in to chapter 4, looking at material balance fundamentals. We're going to be looking at the first few sections of chapter 4, starting with 4.1 and probably getting to about 4.2, 4.3, maybe a little bit by the end of today. On Blackboard, if you want to follow along in terms of slides, we're going to be going through the lecture 2 slides. It's titled Fundamentals of Material Balances. I'll take notes while I lecture today, and then I'll upload those like I did yesterday. So, what we're going to be talking about first deals with process classifications. Now, there's a number of ways in which we can describe a chemical process, and how we essentially label a process tells us a lot about what to expect from its material balance. For example, we can discuss processes that are considered a batch process. What this means is we have some feed that enters the process. Then, after a certain amount of time, the product, or the effluent, will then leave the process. And this is pretty common when we're looking at certain products, things that require high degree of quality control. Typical things like you're going to see fermentation processes. For example, if you want to make beer. Also, pharmaceutical systems. Where you have that high expectations, the high standards. You want to make sure if you're going to be making, let's say, an insulin or ibuprofen, that you have really stringent controls over the product that you're making. And so a lot of those types of processes are going to go using a batch style. Counter to this, we can look at processes that are continuous, where feed is continuously added to the process, and products are continuously removed. And I can, crudely draw it out like this, where I have some feed material. Then I have, a process where that feed undergoes some sort of reaction or change or separation. And let's, I could have product being continually withdrawn from that process, right? And so good examples of this are going to be a lot of petrochemical style processes. And specialty chemicals. And in general, we like to operate processes continuously because it maximizes our productivity, right? Because you're continually feeding things into the process and you're continually able to produce product. And so you have, high degrees of efficiency. Now you're not going to have as high of a degree of quality control as you would compare to a batch process. And that's, one of the, I would say, trade-offs that you have to consider in some processes. And in addition to these kinds of types of process, we have, the batch and the continuous. We can have what's called a semi-batch process, where you have elements of both batch and continuous processing in a single process. A good example of this would be, things like the food and beverage industry, where a lot of food products are going to be initially blended, mixed, heated to some degree as batches. But then once that batch is complete, it is sent off to some form of a continual, packaging, wrapping, shipping system. So you have elements where things are going to be continuously put into the process, but you might have a few elements of that process that operate as batch units. And then once that batch process is complete, then it moves into and acts more as a continuous process. Are there any questions so far? You guys can feel free to chime in with questions, put mentions on the chat. But if not, I will keep moving. So in addition to those classifications, another big delineation that we like to consider for a chemical processes are a discussion between whether it is considered steady state, or we can call it a non-steady state or a transient process. And these two classifications are extremely important. Let's first look at what we consider a steady state process. We can define a steady state process as one whose process variables or conditions do not change with time. And I'm going to put a little bit of an asterisk around change with time, primarily because we can consider a process steady state even if certain values are fluctuating around a common mean. However, if there's no large trend away from that mean, we can still consider it steady state. For example, if I've got, let's say, here, let me erase this transient. Let's say I've got a thermocouple on a tank and it's measuring the temperature versus time. Now, if the temperature kind of deviates a little bit, kind of like this, I can still consider that a steady state process because that temperature is largely fluctuating around a fairly stable mean. And so I can consider that steady state, and I can stay that temperature is stable and constant in regards to a certain process. Now, contrary to that, we can look at processes that are considered transient, where process variables and conditions vary significantly with time. And, going back to that same example, if I wanted to measure a different tank versus time, I might see figures that look like kind of like this. And in this case, I would say that the temperature is not stable, or I consider it transient. And so there's no stable mean. This temperature is completely unstable, and so there must be something occurring within this imaginary tank that is causing this to occur. So this is what would be considered transient or an unsteady state process. In general, a majority of processes are going to have some form or degree of an unsteady state behavior. I would argue it's quite rare to have an entire process nice and stable. There's always going to be some form of fluctuations, like we see in this kind of figure here. The question a lot of times we have to ask ourselves is the stability such that we can consider it a steady state, or is it to the point where we're going to have to argue it's fully transient and if an action is going to be made? For example, if I have, looking at that same example, just because it's easier to visualize, if I have something that looks like this, the question then becomes, is this steady state or transient? Because looking at the mean, there seems to be some deviation in what the mean is over time. And so when looking at a chemical process, it's important to consider whether we can truly make a steady state assumption, or if there is some degree of instability such that that assumption won't be valid. Now, I will state for the majority of this class, we're going to be relying on steady state assumptions, primarily because the purpose of this course is to give you guys good practice and skill development in doing material balances, not necessarily in perturbation analysis. But it is something that I think is worthwhile to consider in terms of what truly defines a steady state process versus a transient process, because it's not as black and white as some people would think, or as I would argue the textbook presents.
You said for this course we mainly focus on steady state.
Yes.
Is the course later on where we focus on transient?
That's a really good question. Yes. Towards the end of The degree path for chemical engineering, for those of you in BME, you'll probably have some of this when you start talking into sensors and sensing. But for the chemies, the class in process control discusses essentially the mathematics, modeling, and application of saying, taking a process that looks like this, and how we stabilize this? Is because you don't want to see something like this and say, okay, the temperature is going up, so I need more coolant, for example. Well, the question is how much coolant? Because if you put too much, then it starts going back down again. It might be going down too much. Because let's say I have a 400 liter tank, and I add cooling to it, or I have like a cooling jacket. It's not going to cool down instantly. That's going to take time. And so that's the hard part when it comes to looking at transient processes, right? Because then we're looking at rates of change and saying, okay, do I need to cool it quickly? Can I wait a little bit? To what degree do I need to cool it? Or, am I going to overshoot it and then my temperature is going to fall too much and then I'm going to have to heat it up again and then I'm going to have something that looks like this. And then I've just essentially added more instability by trying to fix the problem. And so the course of process control says, okay, what's a good method to get it back down quickly but not too quickly and get to the value that we want it to? It's a really good question. The answer is yes, but there's a whole lot of math involved in fixing transient processes, as I would say. So any questions on those classification definitions? Transient, steady state. Steady state, well, when we start here in a second, when I go through, the main mass balance, material balance equation, you'll start to see why we like to assume steady state. And by the end of this course, steady state will definitely be your friend. But any other questions? No? Okay. So let's keep moving and talk about the generalized mass balance expression. Now, if I'm looking at a continuous process, kind of like I said earlier, I can have some feed, my process, where I have a reaction, separation, a little bit of both, and a product being removed from that process. Now, with that, I should have some mass, which I'm going to designate it with an M with a dot on above it, coming in. And hopefully I'll have some mass leaving that process. So it's a continuous process. I've got material coming into the process unit, and I have material coming out of the process unit. If I wanted to write a fully fledged material or mass balance on this overall process, I would first ask myself, well, what's my system and what's my system boundary? For this process, my system is the process and my boundary is essentially the box that I've drawn. So I'm going to draw a little blue box to really describe that. And this is my system boundary. And once I have that in place, I can ask myself, okay, based on that, what is my material balance going to look like? And for any system, I can write an expression that looks like this, where I have input plus generation minus output minus consumption equals accumulation. And I'm gonna put like a big box around this. I'm gonna star it a bunch. This is important. All right. Any material balance can start with an expression that looks like this. So let's break down each of these terms one at a time and ask ourselves, how can we determine what these values look like? So let's start with our input. The input is any material or mass that enters our system. So if this is my system boundary, an input is anything that looks like this, going into that system, crossing that boundary. Next, let's look at our generation term. Our generation term is any material that is produced within our system. And the way I could describe that is if I have a system like this, here's my box, and I have a reaction, A plus B going to C. The generation occurs here. So that 2C is generated within my system and within that process. All right, next we have our output. That is any material or mass, it's kind of the same thing, that leaves the system. Same kind of designation. That, sorry, it would be kind of this way. This is in system, this is out of the system, this is in the system, this is out of the system. I'm trying to be consistent to make it a little easier, guys, to understand my notes. All right, next we have consumption. Consumption is any material that is consumed. I know, these are really good definitions within the process or the system. So if I dry my box again, and here, actually, this would probably be easier if I do the notes this way. There's that, so I'll just draw boxes everywhere. That's why I like using this tablet thing. I can always fix notes really easily. So going back to that A plus B goes to 2C, the consumption would be on the A plus B. Here, I'll make that bigger so it's easier to read. Okay, A plus B goes to 2C, if you can read my handwriting. So in this case, that A and B would be consumed within my system. And then last but not least, accumulation is any material that remains in your system. Let me try to think of a better verb. That's builds up or is lessened. within your system. And I'll come up with a good diagram. All right, so we've got, let me draw our system box again, the right color. Got to be consistent. So the way I'll think of this is if I've got stuff coming in and out, and let's say I've got, it's like a tank with like a certain water level. If over time that water level kind of goes up or down, that is what I would consider accumulation. Material is either building up within that system such that over time there's more and more material in the system, or over time there's less and less material within that system. Does each of those terms make sense? Is there anything that you guys would like me to reemphasize, redefine, redescribe? Or are you guys good? I'll take your silence that you're blown away by my drawing. I'm gonna, coming soon to a modern art gallery is this. Okay, so now that we've got this generalized form of a material balance, input plus generation minus output minus consumption equals accumulation, let's look at this example that we have here and try to come up with a good mass balance, right? So if I've got a process unit with mass in and mass out, I can redefine or put the material balance in mathy terms, as I like to call it, by writing it like this: mass in plus mass generated minus mass out minus mass consumed equals mass accumulated. All right, so I'm just putting everything in terms of mass flow rates, the big M with the dot on it. So I can ask myself, for this process, do I have mass in? What do you guys think?
Yes.
All right, so I do have mass in. All right, good. Do I have any mass generated?
No.
You can go either way if you want to argue, depending on your political ability. I haven't said anything if there's any sort of reaction in my process unit. I've just said it's a unit. I'm gonna say and make an assumption that there's no reactions, so there's gonna be no mass generated. So I'm gonna say no reaction. Or I haven't described anything about my process. So what about mass out?
Yes.
I do have mass out, and I've already said there's no mass generated because there's no reaction, so there's probably going to be no reaction and no consumption. Now, what about accumulation? This is the tricky part, because as I've written it right now, I can say now, well, mass in minus mass out equals mass accumulated. And so the question is there accumulation?
That would depend on the rate, correct?
It would, right?
Yeah.
And so that means if mass in is greater than mass out, there is mass accumulation, right? So if the mass in is greater than the mass out, there's a positive value in the mass accumulated. And if mass in is less than the mass out, that accumulation is negative, or there's a negative accumulation. But if the mass in equals the mass out, the accumulation is 0. Does everyone follow that?
Mhm.
And for these two cases, since there's more mass in or less mass in than mass out, this would be a transient process, right? Because the material within the process is changing with time because I have a positive or negative accumulation. For this condition where the mass in equals the mass out, this is a steady state process. And so that's why we like looking at steady state processes, right? Because this is a big assumption that we make is steady state. And if I can make a steady state assumption, I can say the accumulation is 0. And that's why we say, you know, kind of the rule of thumb for steady state processes we like to call it garbage in equals garbage out. And that's why I call it accounting for engineers. If we consider it steady state, what goes in must be accounted for in the output or something's happened. You either don't have a steady state process or you've got a leak in your plant and you better go find it. Or something's about to blow up, one of those cases. None of them are good. Any questions on that generalized expression?
What did you say happened to the mass
The consumption?
consumption?
Yeah, for this, I was assuming there was no like reaction within that process. I didn't state it. So if there's no generation from a reaction, there's going to be no consumption by a reaction.
Okay.
So let's look at an example. And you guys can help me with this. So let's say that we're doing a census on Memphis. And we're going to say that currently, if I could spell, in 2020, I don't know, how many people do we, there's 1.5 million people in Memphis. And we estimate the following. We have 200,000 people are going to move to Memphis. And we expect 350,000 people are going to leave Memphis. Then we expect 75,000 people are going to be born, and 55,000 people are going to die. Too soon. So then the question is, at the end of the year, based on this, how many people will live in Memphis? At the end of the year. Well, let's look at the values we have. We can say we have an input plus generation minus output plus consumption equals accumulation. So if we know the net accumulation, we can know the net population by the end of that year. So I have 200,000 people moving to Memphis. I had 75,000 births. I had 350,000 people leave. And then I unfortunately had, what did I have? 5,000 people pass away. So what is my net accumulation for people in Memphis?
I have negative 130,000.
All right, so Memphis lost a lot of people. Apparently Nashville's up in their game when their bids to get people to come move. All right, so Memphis lost about 130,000 people. All right, so that's the negative accumulation that we see. And so when we're looking at the net population, we have that 1.5 million, is that right? Minus 130,000 or 0.13 million, or we have 1.37 million people in Memphis by the end of the year. Not so bad. A lot of people.
On the top equation, did you mean to put minus consumption?
For this? For the negative?
No, above that, the equation above that.
Oh yeah, that should be net minus, thank you. Yes, that should be minus. And so we have 1.37 million people left in Memphis. Any questions on that? No? Okay, let's take a look at another example. This example will be on mixing two streams. So if I have a manufacturer, and this will be the example in the PowerPoint that I had prepared. We have a manufacturer blending lubricating oil by mixing 300 grams per minute of number 10 oil with 100 kilograms per minute, excuse me, they're both kilograms per minute, of number 40 oil in a tank. The oil is going to be well mixed and withdrawn at a rate of 380 kilograms per minute. And if we're assuming the tank begins empty, how much oil will be in the tank after 1 hour? Now, keeping with good problem-solving practices, the first thing I always like to do with most problems is draw a diagram or flowchart. So I'm going to have my tank, and I'm going to have two streams coming into the tank and one stream leaving the tank. My number 10 oil is coming in at 300 kilograms per minute. My number 40 oil is coming in, I believe, 100 kilograms per minute. It's a tank. It's well mixed. I'll put a little mixer in there for good measure. And I'm withdrawing that blended oil at 380 kilograms per minute. So I blended oil. We can call it number 27. So then the question was, how much oil remains in the tank in 1 hour if the tank started empty? All right, so we can set up our material balance. We have input plus generation, which I'm just going to call gen, minus output, minus consumption, equals accumulation. Now, which of the terms can I neglect in this problem?
Consumption?
We can neglect consumption. Anything else?
Generation.
We can also neglect generation. So we're left with input minus output equals accumulation. So for this problem, I have two inputs, a number 10 oil and a number 40 oil, and one output, my blended oil, which I've called number 27. So if I wanted to find the net accumulation, I would just set the input minus the output and say I have 300 kilograms per minute of oil plus 100 kilograms per minute of oil minus the output, which is 380 kilograms per minute of oil, equals that accumulation term. And so my accumulation, therefore, is positive because my input is greater than my output, and I have a net accumulation of about 20 kilograms per minute of oil. Meaning, after 1 hour, if I have 20 kilograms per minute accumulating, I can say my net accumulation is my accumulation rate, or 20 kilograms per minute, times my desired time that I'm considering, which is 60 minutes, or 1,200 kilograms. Any questions on that problem?
So there was no need for the generation and consumption because there was no reaction?
Yes. Yeah, so in general, some rules of thumb, these are on page 86. If your balanced quantity is a total mass, we can set your generation and consumption terms to 0. Because even if there's reactions, if I'm not concerned about individual components within my system and I just want to care about total mass, I can neglect my generation and consumption. Because outside of any sort of crazy nuclear chemistry, the mass is the mass. And another rule of thumb is if there's no reaction. Oh, pen's getting a little weird. We're dealing with non-reactions with non-reactive species. You can set your generation and consumption terms to 0. So those are some rules of thumb in addition to that steady state assumption that I gave you that you want to just keep in mind. But very good questions. Any other questions or things that I can further clarify? No? All right, let's look at one last problem for the day. Look at example 2 in that PowerPoint presentation. This is a balance on a distillation column. So in this problem, I'm looking at 1,000 kilograms per hour of a benzene toluene mixture containing 50% benzene by mass is to be separated by distillation into 2 streams, a distillate at the top and a bottoms fraction out the bottom. The massive flow rate of the benzene in the top stream is 450 kilograms per hour, and that of the toluene stream in the bottoms is 475 kilograms per hour. So assuming the process is operating at steady state, draw a flow chart, write material balances for both the benzene and the toluene, and calculate the unknown component flow rates for the distillate and bottoms output streams. All right, so let's take a look at this process. The first thing we can look at, drawing the distillation flow chart. So I got a little distillation column. I got my feed, which is a benzene. Here, I'll do this at the bottom. Toluene mix. And then out of the top, I have a distillate, and out of the bottom, I have my bottom streams. The problem states I have about 1,000 kilograms per hour coming in. And out of the top, I have 450 kilograms per hour of benzene. And out of the bottom, I have 475 kilograms per hour of toluene. This tells me I have an additional unknown amount, so I'm going to call it M1 kilograms per hour of toluene coming out the top 2, and another unknown value here, M2 kilograms per hour of benzene coming out the bottom. So I've got my flowchart created, and I can now write material balances for both the total mass leaving my system, which is this column, as well as component material balances for both the benzene and toluene individually. All right, so looking at this as a separation, it's a non-reactive species, and I'm also assuming this is operating at steady state. What that tells me is that for benzene, my input minus my output equals 0. There's no generation or consumption. We're dealing with not a reaction. And this is steady state, so there's no accumulation. And also for my toluene, I can write the same balance. Input minus output equals 0. The same balance applies. Now let's write things a little more specifically, looking first at the benzene. Since the input minus the output is equal to 0, I can also consider the input equals the output for both systems. So if I was going to write a material balance for the benzene, I would state, well, the input is 1,000 kilograms per hour times the mole fraction or the mass fraction of benzene in that stream. That has to equal the mass flow rate of benzene coming out the top, which is 450 kilograms per hour, plus the flow rate of benzene leaving the bottom, which is an unknown currently. So I have an M2. Now, for toluene, I can write a balance as well. I have the same input, 1,000 kilograms per hour, but now I'm looking at the mass fraction of toluene in that feed equals the output leaving the top, which is currently unknown, M1, plus the amount leaving the bottom, which is 475 kilograms per hour. So as it stands right now, I have 2 equations and 4 unknowns. However, in the problem statement, it said that 50% of the benzene by mass, it says that the feed contains 50% of benzene by mass. This means that the mass fraction of benzene is 0.5. And since there's only benzene and toluene in the system, the mass fraction of toluene is also 0.5. So I can rewrite each of these material balances like so. And so if MB is 0.5, I have 500 kilograms per hour equals 450 kilograms per hour plus the mass M2. That tells me that M2 is 50 kilograms per hour of benzene. And for toluene, I have 500 kilograms per hour equals M1 plus 475 kilograms per hour, or M1 is 25 kilograms per hour. So now that I have these, if I want to, I can go back and say this is equal to 50 kilograms per hour, and this is equal to 25 kilograms per hour. And I could also ask and answer, the question is, what are the material mass fractions of the top and bottom streams? Right? Which means if I'm looking at the top stream, the mass fraction of benzene is going to be 450 kilograms per hour over the total flow rate leaving the top, which is 475. And the fraction of toluene in that stream is going to be 25 kilograms per hour over 475 kilograms per hour. So what do these two values equal? Now, let's see. I got about 94.7% here, which tells me this should be 5.3%. So for the top stream, I have 94.7% benzene and 5.3% toluene. And looking at the bottom stream, doing that same analysis, I have 50 kilograms. Let me look at the bottom really good. 50 kilograms of benzene over 525 kilograms per hour total. And for toluene, I have 475 kilograms per hour out of 525 kilograms per hour. Or 9.5% benzene and 90.5% toluene. Any questions on how I was able, now that I had solved the material balance for all the flow rates, could then look at things in terms of material compositions for those output streams. Looking at the flow rates of the individual components compared to the total flow rate gives me the mass fraction of those components in those streams.
Since it's a mass fraction, do we need to make it so it's not a percent of the stream for the answer, final answer, or?
If you wanted to be really detailed, you could just say, we call that a weight percent.
Okay,
So, we can just say, instead of just percents, we could say weight percent, which I always just designate WT percent, which is a little different than mole percent or volume percent. But that's a fair question. I'm not as picky in terms of that. Some people might be, but that is a fair question. And if you wanted to be, extra careful, you could just designate them as weight percents, and that'll just tell me that those are mass percents or mass taken from mass fractions.
okay.
And I guess since I wrote it as percents, I can say times 100 to be entirely accurate, because that just gives you fractions without the 100. All right, does that make sense? Good clarification. All right, well, that's all I wanted to talk and cover about today. I will have office hours this afternoon for those of you that have questions, either on homework or just kind of getting through this. But thank you guys all for attending. I appreciate it. And take care. Good luck. And I hope you're enjoying the class thus far.
Have a good day.
You too. You take care.
Right.